So this is assignment 4. The first part is to implement a linked heap. The basic principle of the linked heap is the same as the traditional one, which is to build a tree structure and to make sure every parent is smaller than its both children's, and also make sure this is a full tree. And whenever I need to delete a node, I delete the root of the tree, and that will be the smallest of the whole set. And then after that, I promote the one of the leaves, and then do the swimming down. So similar to whatever we learned in the class. During the implementation, the most difficult part is to find out the correct position of the last node when I need to do the insertion or to do the deletion or do the promotion of the last nodes after deletion. So in order to do that, what I did is I defined a pointer to a node I call the last node. Well, it's actually the parent, the last parent node. So whenever I need to insert a new node, it will be one of its children. Whenever I need to delete, it also will be one of its children. So these two functions, the move last and revert last, will be the two most important function for this implementation. So what it did is whenever I insert one element, I need to determine whether I need to move the current pointer of the last node. And so in some case, it will just move to the next node, next neighboring node to tell me where I need to insert my next node of this whole tree. And this is similar to the reverse last, it is similar to the move last, but in the reverse direction. This will happen, will be needed when I'm starting to delete nodes in the trees. And the other function are pretty much standard, similar to what I already have in the standard minimum heap. So here I have a float function. So basically it's just used to moving up uh, um, it's just to moving up a node, and a sync function is just to moving downward a node. And here I'm having defining a swap function to support both the float and the sync function. It's just to swap the current parent node and one of the child node. And yeah, well, because we have a lot of links between in this tree, so we need to this function is one of the longest one in this implementation. And so that's pretty much once all of this, all of the float and all of the last, all of these functions are implemented, the insertion and the deletion are pretty much trivial. And so here is the demonstration of this linked heap. And as we can see during the testing, what we did is just to insert all of these nodes from 4 to 623. And the min heap will do the ordering, well, partially ordering within the data structure based on the keys I insert. And once I start to delete things, it will always remove the root, which means it will always give me the one element with the smallest key value. As we can see, that's exactly what being outputted in the screen. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all of the keys being deleted from the min heap in the order. So this is for the min heap part. The next part is the priority queue. So once the min heap is being implemented, priority queue is pretty much straightforward following the implementation. So it first just to also import the linked heap, and then the functions I need, the add, remove, and min, just to look into the min heap and see which one I need to do. For add, I just need to insert a new node into the min heap, and the heap is going to do the work for me to determine where this new node should locate at. And the remove is just to delete the root of the current min heap, and also get return that root node, use that root node as a return value. That's where I return here in the remove function. For the min one, it's just like pick at the root of the min heap. Here I have the get element function defined in the binary node to support that function. And the length of the min heap is just being defined also here as a size. So I'm defining a size variable to keep tracking of how many elements I'm currently having in my priority queue. By the way, this could also be implemented in the linked queue, but I want it to be more direct. So I put it in this top level data structure. And this is a demonstration of how, last part is to demonstrate how the priority queue is working. So, so there we see, we have the we have 7 nodes being inserted into the priority queue. We have, and they are in, because the keys are different. So when we start to remove, it will be the ones with smallest key values to be removed first. As we can see, that's exactly what happened. We have 4, 4, 5, 5, and 6, 6 being removed in that order. So which means this priority queue is working as we intended. So that's assignment 4. Thank you.